limits by constructing an appropriate table of values, then determine the exact value by using algebra. And then we want to plot it. So we're kind of looking at it from the three perspectives that when we study limits, there's a numerical point of view, a graphical point of view, and an algebraic point of view. And also, if you can describe it in words, that would be great. So let's do the first one. When we're doing this, we're going to need technology, a table. It'd be nice if we actually had a, I think Excel would work well, or one of those spreadsheets, but I'm assuming we're just going to stick with our calculators. So let's take a look at how to do one of these problems. We want to approach 1. And so what we want to do is make a table for this where we put in some certain key values that get closer and closer to 1, and then we try to look for the f of t value. And then we're going to plug in values near 1, but we can't really put in exactly 1, because if you put 1 in for t, we're going to get 0 in the denominator. So whenever we get zeros in the denominators, we're always a little worried about that. There's still a chance that it could exist. Doesn't, they tell you not to divide by 0, like it's really bad. But just because the denominator is 0 doesn't mean it's not going to exist anymore. Yeah? Yeah, so that's the algebraic part. And so I think they want us to approach this 3 different ways. So the first way, we'll do it numerically. Now, numerically, we want to get to 1, but we don't want to get exactly at 1. So if you look at a number line and you see 1 here, think about getting closer and closer to 1 from either side. So if I put a number, if I get close to 1, this is kind of blown up number line, like 0.9. And then maybe 0.99, and then maybe 0.999. Those are all numbers that are getting closer and closer to 1. So let's start with those 3 numbers. And then we're going to, we could do this by hand, but I'd rather use a calculator, punch stuff in. And then we're going to come from the other side as well. So something that's a little bit bigger than 1. Like 1.9 or 1.1, sorry, and then 1.01, and then 1.001. So those are all numbers that are getting closer and closer to 1. The 99s are coming from the left side, the 001s are coming from the right side. So those are good values to check. Now let's take out our calculators, because we're not going to do this by hand. And then we're going to try putting in these values. So are you guys familiar with the table setup for this? So important thing to be able to do is to put in the function correctly. And because there's adding and subtracting in the numerator and denominator, parentheses are going to be really important. So let's, I'm going to clear my first one, y1, and then I'm going to put in parentheses. Now it says t, but when you're graphing things in the graphing calculator, thanks, Victor. When we're graphing things in the graphing calculator, this particular graphing calculator has x as the independent variable, so just keep that in mind. And don't forget about the parentheses. So this worksheet is for later. Like I said, maybe at the end of class, or maybe you guys deal with it tomorrow. All right, does this look okay? Looks like the parentheses are in the right spots, and then the divide by sign is in the right spot. All right, now let's set up a table. I'm going to say second function and table set. Now this has an automatic setup for the tables. So I press second function in Windows. I think for the independent variables, I want to ask, and for the dependent variables, it's auto. And then this table start and table step doesn't really matter if you got this set up. So that's good. And then instead of hitting graph, I'm going to press second function in graph, and then that'll be a table. Now I have some values here already, but I want to put in the values that I have, like 0.9, 0.99, 0.999. And I kind of see a pattern over there, and I'm going to go with 1.001. And then notice if you, just for fun, let's try to put 1 in, it gives you an error, right? So that's what we have. Now, based on the table that we're looking at, does it look like there's a nice guess as to what the value should be? What do you think it should be? Looks like it's teetering between 1.999 and 2.001, right? So it looks like it might be 2. Limit as t approaches 1 of that function is equal to 2, according to our numerical analysis. Is that cool? Now, let's try to approach it from a graphical point of view. Now that we have the graphing calculator all set up here. Whoops. This is a nice picture. Let's save that picture here. What did I say? Graphic. So we want a graphical point of view. Let's take our calculators out again. And from a graphical point of view, we just want to make sure it looks like it's near 2, right? Based on our numerical analysis. And when we set up, before I graph this blindly, I want to take a look at the window because I have some idea of what the window might look like. And I want to make sure I surround, on the x-axis, I make sure that 1 is included. So 0 to 2 or negative 1 to 3, something like that. Let's try negative 1 to 3 for now. So that's my x values. Now my y values have to include 2. So maybe go from 0 to 4 for now. And then, oops, that's not where I want. I want my scale to be 1, not 14. Okay, my y min is 0, and my y max is 4. And also a scale of 1. And then I think that's it. Let's graph it. Now you have this trace function. Oh, you can kind of, I don't know if you can see it. I can kind of see it on my computer. Looks like there's a little break here. If you hit the trace function, you get to move around. Let's try that again. Did I do that right? Trace. Oh, those are plots. Sorry. Okay. So you can move this around to try to get some idea where you are. And you can actually type in numbers, right? Like 0.9. And then we get a y value that comes out. You can type in 2.001. We get a y value that comes out. No, we want 1.001. We get a y value that comes out, and we can punch in numbers during our trace to get our values. And then if you try to type in 1, we know that that's not a good point, right? And so 1 here, the y value has nothing to offer. And when we did the table, it actually said error. So this is, from a graphical perspective, though, it looks like if we move a little bit to the left or a little bit to the right of 1, we're still hovering around 2, which is what we saw in our number line. So from a graphical perspective, it looks like we're on the right track here. Oh, come on. Red. Graphical perspective, it looks like when you're near 1, you're hovering around 2. So this still looks like it's going to be our limit. So to kind of interpret this, you can also, if it wasn't clear yet, you can also take your calculator and zoom in. Zoom in, and it's asking you to pick a point to zoom in from, and then just hit enter. So in this case, it looks like the image is going to end up being or looking like a line, and it looks like it's still near 2. Okay, so from a graphical point of view, you want to trace a little bit to the left and a little bit to the right of your point, and then see what the y value is near. Okay, now the algebra. So this is kind of the best way to prove, or the algebraic way to prove, that a limit does exist. So we'll take a look at the limit as t approaches 1 of t squared minus 1 divided by t minus 1. Now, if you're going to just do some algebra, and you have not taken the limit yet, you should leave the limit symbols here, and then do the algebra that you need to do. And so we had a suggestion for dealing with this. What was the t squared minus 1 equal to? So the numerator just becomes that, factors out, and then we can just take the canceling stick and cancel that out. And then we have the limit as t approaches 1 of t plus 1. So now there's no denominators. There's no issues about dropping that number t in for the t in the function. So t is equal to 1. When we tried to put it into the earlier graphs, to the earlier function, we had a 0 in the denominator. Now there's no 0 in the denominator. Algebraically, it's supposed to be equivalent. So I can put the t in there. And by putting the t in there, we're just going to get 2. Which is what we saw from a numerical point of view and what we saw on the graphical point of view. So the idea is to be able to do this in 3 different ways in case it's almost like algebraically impossible, maybe really, really difficult to work with it algebraically. Then we can use the numerical or graphical methods to figure it out. Okay? All right, so we went through that in a lot of detail. Do we still want to do one more, B or C, or should we move on to a different problem? Let's do C, and you guys will do B, and hopefully it'll work out. So this time we'll do C. So numerically, I'll run through this really quickly since we already did an example. So let's do the numerical point of view. And we need to make sure you enter the function correctly. That's probably going to be the biggest part of this problem. So I need the square root symbol, x plus 1. And then divide by just x in the denominator. Oh, wait. Oh, I have to do a minus 1. Oh, I need parentheses. So x plus 1 under square root minus 1 divide, oops, close parentheses, boy, divide by x. We're hovering around 0, so let's adjust the table set. Actually, the table set's already worked out, so let's make a table. So it's around 0, so I want to put negative 0.1 maybe. So minus 0.1, minus 0.01, minus 0.001. 0 is going to give me an error. I'll put 0 in the middle this time. And then 0.001, 0.01, 0.1. Can you guys see? So 0.50013, 0.49988. Well, there's a pretty good looking candidate there, right? What do you think it should be? Any ideas? No. What? 0.5? Right? A little bit up here, it's 0.5001, so it's a little bit bigger than 0.5. Down here is 0.49998 or 9988. It's a little bit less than that, so it looks like 0.5 might be the winner here. But right now it's just an estimate, so we're going to look at the graph to see how it is, and then maybe do the algebra part to confirm that it actually is 0.5. So let's take a look at the graph. We have the function already in there. I just need to set up the visual so I can see the graph. I want to make sure that 0 is included, so I want to go from a negative number to a positive number. So a negative 1 to 1 is probably good enough. The scale, we can just leave the scale at 1. The y values, it looks like it's 1/2, so I can go from 0 to 1 or negative 1 to 2, whatever might look nice so that the thing is right in the middle. You know what? It doesn't really have to be right in the middle, so it doesn't matter. So let's go with 0 to 1, because we know 0.5 is right in between. So let's graph it. Okay, so we could zoom out also or zoom in to take a look. And remember, the key is to hit the trace button. So if I trace around, I have a, let's try putting in one of the numbers that we actually had, like negative 0.01. So I got that 0.5, and then I'm going to right arrow a little bit to see what happens. So it looks like it's hovering around that 0.5 space. So look at the values. This is near 0. This is close to 0.5 right here. All right, so let's do it algebraically and confirm. Hopefully, it actually is equal to 0.5. So if we do it algebraically and we don't get 0.5, then something's wrong. So let's write this down. Limit as x approaches 0 of the square root of x plus 1 minus 1 divided by x. So the first one was pretty easy, right? Just factor it out. Here we have a square root. And when we have a square root and then we want to change the appearance of this thing, the usual thing to do is, does anybody know what the usual thing to do is? Multiply by? No, not quite. Another guess? Another shot? Not throw away your shot. Something with a square root. The conjugate. Yes. The conjugate is a tool that they usually use in complex numbers with the imaginary number I. But it's a way to, usually in algebra, maybe, if you have a square root in the denominator and that you're adding like this, you multiply by the conjugate so that you can, quote, rationalize the denominator. Here, what we're doing is we're rationalizing the numerator, and not because we don't want any radical signs in the numerator, but because there's a way to simplify. These things actually simplify. Now, I can't just multiply the numerator by this. I have to, multiply, keep the expression to be the same. So I would also multiply it by the denominator so that I can keep this as an equivalent expression. So I'm essentially multiplying by 1, and if you multiply by 1, you don't change anything. All right, so if we multiply by the conjugate, I haven't taken the limit yet, so I'm going to continue to use that symbol. Now, if we multiply the conjugate, it's like foiling a difference of two terms. It's like a minus b times a plus b, right? In fact, from the last, how we factor it from here to here, it's like multiplying this together, so it's really the difference of the two squares. Can I just say that? And what I mean by the difference of two squares is that this numerator will just be the square of the first term minus the square of the second term. I mean, you can FOIL it out. You'll see the two middle terms will cancel. But that's what's going to happen. Now, this one, unfortunately, can't do anything about because, well, you can't. So it'll just stay like that, and hopefully it'll still simplify. So what's neat about these types of problems is that the numerator, and usually these problems are set up so that it actually will work out. If you notice the numerator, you get x plus 1 for the first expression, and then the second expression has a negative 1. So the 1's cancel, and we just have x in the numerator. And that's good for the x in the denominator because you can cancel with that as well. So this x and this x will cancel after 1 minus 1. After you subtract 1 minus 1, you can cancel the x and x. And then so you have limit as x approaches 0 of nothing on top except for a factor of 1, and then the square root of x plus 1 plus 1. Now the good thing is that when you put 0 in now, it's not going to be a 0 in the denominator anymore, I hope. So if you put 0 in here, you got the square root of 1, which is 1, plus 1 is 0. So let's drop that 0 in there. And then we get 1, well, we get 0 in there, and you're going to get 1 over 2, which is what we were expecting, what we were hoping for. And there you go, 0.5. So now we're able to do it algebraically, and that confirmed the estimates that we had from the numerical approach and the graphical approach. So there's a few tricks for these limit problems, and we just saw 2 of them. The first one is just factoring, and the next one that we just saw here is multiplying by the conjugate. There's a few other tricks that you need up your sleeve to be able to do some of these other interesting limit problems. Okay? Well, good? Does it look cool? Look easy? Look fun? Looks like you want to go home and do some more? Or you just want to go home? All right, we're good with number 5. What is that for? Whatever that was. That was number 4. Anything else? I guess there's a 7 also. What do you think? Are you guys supposed to work on this in class? Or at home, outside, in class? Should you work on it, and or should I do it? I don't want to take your thunder away. All right, let's pick one, 6 or 7. I'm just going to do one more, and then we'll try to move on to just to give you a preview of what the next chapter is about. What do you think? 7. Yeah, that one doesn't look nice. I did want to talk about absolute values, though. So it says here to sketch a graph on the axes that has the following properties. So f of negative 1 is equal to 3. By the way, this is like a really common problem that you'll see in your calculus book. Hughes Hallett book has these kinds of problems a lot. Okay, so f of negative 1 is equal to 3, and then the limit as x approaches negative 1 is also equal to 3. F of negative 2 is 2, but the limit is going to equal to 1. F of 1 is not defined, but the limit as x approaches to 1 is 0. And then f of 2 is equal to 1, but the limit doesn't exist. So we've got a bunch of weird scenarios here. The first scenario is a scenario that describes a nice, smooth, continuous functions. The other 3 bullet points over here show scenarios where the limit might exist, but the function itself is not continuous. So, so let's start with the first one because it seems really easy. I need to go find negative 1 somewhere. If this is negative 3, maybe I'll make it this a little bit bigger. see what I'm doing here. So f of negative 1 is equal to 3, so I can safely put a dot up here, say that's part of my graph. And then the limit as x approaches that is going to be 3 also, so looks like it'll just pass through there. So that's the nice one. That's the nice point. F of negative 2. F of negative 2 is equal to 2. 1, 2. Negative 2 is equal to 2. But the limit as x approaches negative 2 is 1. To prepare for this idea, you can put an open circle there and to say that the graph as it comes from the left should equal to 1, and the graph as it comes from the right should equal to 1. So it looks like this part of the graph should look something like this. It'll be passing through the point negative 2 comma positive 1, but there's going to be a hole in it. The limit exists there, but the point is not defined there. So that's how that part of the graph should look like. The next one, f of 1 is not defined, but the limit as x approaches 1 should equal to 0. So if the limit exists, but it's not defined, it'll be like that circle. So at negative 2, the limit does exist, and it's defined, but it's defined somewhere else. So I'll have that circle here, and I'll define the dot somewhere else. At 1, f of 1 is not defined at all, but the limit should equal to that. So I want to connect this. I'm eventually going to want to connect the graph so that it's just one graph. So I'm going to make this going up because I want it to go up to 3. Okay? Yes? So an open circle means you got points getting closer and closer to that point, and that point that we're looking at here is the point negative 2 comma 1. So the graph will get closer and closer to that point. But the function itself is defined at positive 2. When you plug in negative 2 into the function, it gives you an actual value of positive 2. So yeah, that's the first group, the green one. The limit approaches negative 1 is equal to 3. And because the function itself is defined there, it's a dark circle. Okay? Now, the next one, f of 2 is equal to 1. So f of 2 is equal to positive 1. But the limit doesn't exist. So there's several ways to play this game. One, if you like infinity, you can make the limits go off to infinity. Two, you can make it go approach an actual value from one side and make it approach a different value from the other side. So there's a couple of ways to do this. So one way is that maybe the limit might be approaching 2 from the left side, but then from the right side it goes somewhere else. So would you agree that this now, as x approaches 2, the limit does not exist? So that's one way for this to not exist. Okay? So let me connect the graphs, and then I'm going to show you, using the same pictures here, I'll show you ways where you can... I'm assuming this is supposed to be continuous, but... So, this is okay? It follows all the bullet point procedures. I mean, the criteria. Yes? Which part? I'm just guessing. Why don't we, oops. Why don't we try it again? All right, so I'm going to try it again with a different perspective. Let's say yesterday I did the graph the way I did it, and then tomorrow this is probably how I might do it. So I'll go through the same things kind of quickly this time. And -1, what was -1? That was green. -1, I'm at 3. At -2, it's at +2, but then there's a hole. So I might connect it a little bit differently this time. At +1, it's not defined, but there's a hole. What color was +1? Purple? Purple. There's a hole at 0, so I know I'll be approaching this. And then at 2, it's equal to 1, but it's not defined. So it's not defined. One way to say something's not defined is that if they have two different limits from the left and from the right. The other way it's not defined would be, well, to just let this go off like an asymptote. And I can have the asymptote coming from the bottom as well, or coming from the top. And then I can do more wigglies here if I want. So there's different ways to approach this, as long as it satisfies the same criteria. Yeah?
So just to be clear, so like the point, so only a point can be defined and a limit doesn't exist. That's how you pair them?
No. A point can be defined. The limit might not exist.
Oh.
There could be combinations of these things.
I mean, like, yeah, I understand that, but like, can a limit be not defined, or does that just mean it doesn't exist?
Some books deal with it differently. If you go off to infinity, Some people say the limit exists and the limit is infinity. But this one I made sure it wasn't just infinity, because what come from the left it went down to infinity, negative, and from the right it went to positive infinity. If they both went down to negative infinity or both to positive infinity, then there's a possibility that somebody can say, oh, the limit exists and is equal to infinity. So sometimes when they say limit is infinity, sometimes they take that as an actual value. But it depends on how you want to approach it, how Professor Hoffman approaches it, or how the textbook approaches it. Okay, anything else? All right, so the other problems are, that one with an absolute value problem, I think it's a good problem to work on. And I don't know if you guys know how to do the absolute value in your calculators. Do you know? So there's an ABS function in your calculator that stands for absolute value. And I don't know how to get to it directly, but there's a second function in math. Or no, you don't need a second function, at least not for my calculator. Let me undo the second function. If I press math, and NUM number is absolute value. So that's where the ABS is. So if you want to try to graph something like that, you would do an ABS. So math, number, ABS, x minus 3. So this is this is the way you access the absolute value function in your graphing calculator. Also, the absolute value has a special definition. It's equal to positive x if x is bigger than 0, negative x. So that also will be important for the numerical perspective. All right, for the last 7 minutes or so, I want to take a look at the other, just to give you guys a peek of this. So the idea behind this now is the limits. I think the idea of limits is the beginning of calculus. Now this is moving towards the idea of a derivative, and then you will use limits to explore this. But you're going to use some algebra and pre-calculus work where you have to find equations of lines, and then you want to find the slopes of those lines. So let's do a piece of this problem. I know I probably should let you guys work on it, but we don't have too much time. So let's take a look at it, and then you guys can carry on with the rest of this stuff. So here's your function and the graph of your function. So they're asking us to label 6 distinct points on the graph, including 3 points that correspond to when the ball was released, when the ball reaches the highest point, and when the ball lands. So I'll let you find 3 points. I'm just going to mark the 3 points that they're asking for. So the ball was released at time is equal to 0. Ball was released. The ball reaches the highest point. And then the ball lands. I'm assuming that this is the height, so when the height is equal to 0, then it lands. So you want 3 more points to label, so label them anywhere on this graph, whatever might be convenient for you. Does it look like a transformation of some basic function? What's the basic function? X squared. I'll use t. So t squared, the t minus 1 probably means it got shifted over by 1 unit to the left or to the right? To the right. The negative in front of the t squared made it go upside down. And the 64 out here made it shift up 64 units. So we have a couple more clarification points here. We have the point, the x value is 1, and then the y value is 64. Okay, it says here, in everyday language, describe the behavior of the ball in the time interval from 0 to 1 and on the time interval from 1 to 3. What occurs at the instant of t is equal to 0? So I want you to take a minute, see if you can write down some words. So this is a good time to think about how to say this in words, and that's part of, I think, math. That's what's important in math, is be able to explain things in words. You can't just do a problem and say, oh, I just did it. I don't know what I did. All right, what are some words? What can you say about the interval from 0 to 1? What can you say about the ball? Anything else? Okay. That's good. How about an interval between 1 and 3? What can we say? Spell that right? Decrease? How do you spell decrease? S. Anything else? Okay. And what occurs at the instant equal to 1 second? What's happening with the ball? Seems like it, huh? So let me highlight the key words I think that he will be looking for, he, Professor Hoffman. I think this whole idea of increasing, another word for falling would be the opposite of increasing, decreasing. And then the ball seems to be at rest. It's neither increasing nor decreasing. So I think these are the keys that you're going to want to focus on when we start dealing with derivatives. Okay? All right, so I hope you got something out of today, and I hope Professor Hoffman gets better.